All right. Good morning, everybody. I'm Çağlar Elbüken. I will be emceeing this today's event for you. And before we start, I would like to welcome all of you, dear rector, dear distinguished guests, dear colleagues, friends, students, and dear guests. It is my privilege to welcome you to NanoDay 2019. We have organized a full day of activities for you, and as you might have known, UNAM NanoDays have been attracting quite a lot of attention. This year's event is no exception indeed. Although this is not the best timing for some other universities, we got almost 250 registrations for the event, and we are blown away for the turnaround. And you do have the program at the back side of your name cards. And as you might see, we have prepared a little bit more relaxed program for this year. So there are long breaks with lots of coffee in between. Also, I hope you can get one of our annual reports during the day. Please do check our annual report as well. And as you may have noticed, we have updated our nano pictures and the posters. We have moved the posters outside, so there will be plenty of time where you can visit the posters, talk to the researchers, and I hope that will give you a good idea of the unique blend of research that is going on at UNAM. And in the afternoon, we will also have the flash presentation sessions by a selected group of posters. I hope you are all very excited about that event as well. And by the end of the day, we will be having the open house and open labs. For those of you who has been visiting UNAM the first time, if you want to visit UNAM labs, if you want to learn more about the UNAM programs and the structure here, please do sign up at the registration desk, and I will be providing to you more information about the open house at the end of the day. And once again, I would like to thank you for your attendance, and I would like to thank the organizing committee for making this event possible, as well as our administrative personnel. They did an excellent job putting this event together. And the last but not least, I would like to thank our distinguished speakers for joining us for today. And without further ado, I would like to invite to the stage our director, Professor Hilmi Volkan Demir.
Well, thanks, Çağlar. So a very good morning on this sunny day on our beautiful campus at Bilkent, and a very warm welcome to our annual NanoDay event at our national lab, UNAM at Bilkent. Dear Rector Atalar, distinguished keynote speakers, guests, colleagues, and students. In my opinion, knowledge is power. There exists a never-ending transnational competition of knowledge. Whatever we do or we don't do, the essential questions actually remain. Where do we stand? And where shall our next generations continuously be in this competition? In my opinion, as a member of Bilkent community, Bilkent UNAM stands out as an excellent peak of knowledge in this country, in the region, and is connected via superhighways to many peaks of excellence around the globe. To serve this purpose as a national lab, Bilkent UNAM should and will continue generating cutting-edge knowledge, developing pioneering technologies, and grooming leaders of the future in this country, as indeed exemplified in many success stories of Bilkent UNAM over the past 11 years since its establishment. This morning, you have received copies of our annual report, in which you will find our mission and vision clearly outlined and shaped as a new national lab model at UNAM, along with the candidates, the activities, achievements of UNAM, strategies in the last year, and those accumulated over the years. I think you will see in every page of this annual report of course from different perspectives, that UNAM strives for excellence in science and technology. And indeed, doing so, surely enough, UNAM is reaching out to potential partners and working with the partners joining UNAM's vision and vision on campus in the country and worldwide. Therefore, our motto is excellence in science and technology. The motto, everywhere you see, together with UNAM. This is really to align us inside and outside and to work collectively towards this very end goal. Over the years, UNAM has grown and expanded into 2 buildings plus a separate lab, covering a total of lab space over 10,400 meters square, open to the entire R&D community on campus, in the country and in the region. Now, UNAM houses a total of 87 labs with over 400 instruments. UNAM has accomplished over 95% up and running time for its core facilities. Fostering our R&D landscape, UNAM delivers creative and innovative infrastructure management support, including UNAM Integrated IT Platform System, UNAM IS, for equipment lab project managements, which are now being commercially sold. PI's own UNAM IS budgeting system, UNAM Store, and UNAM Rentals, among others. And with these, in my opinion, UNAM enables an extraordinary track record of success that today we see flourishing collectively at Bilkent, and I think now even outside Bilkent, with UNAM's success impact actually crossing the borders of this campus, increasingly more touching and shaping the future of promising researchers, institutes, universities, and companies. Again, working collectively toward the optimal of this country in this competition of knowledge. As of today, UNAM members have collectively undertaken and are currently carrying out a total of 216 R&D projects, won 127 awards, 68 national and 59 international, and completed 421 theses at UNAM, leading to over 1,200 SCI journal publications and 93 granted patents, 51 national, 42 international, 46 of which contributed to commercialization, along with 171 patent applications, 110 international, 161 national in the pipeline, making major contributions to the R&D impact. To date, enabling important technological innovation and entrepreneurship, UNAM has generated 21 spin-offs, among which we have great commercialization successes, including AI technology, NanoDay scientific, InnoCode, to name a few, and more surely on the way. UNAM has now started hosting corporate and startup labs at UNAM, coming actually from outside Bilkent, including Turkish Aerospace, TAI TUSAŞ, Cannes, and Gez Biotechnology, among others. Including our UNAM Talent Program, attracting very promising and rising star young principal investigators across the country, UNAM has now 393 researchers and staff. UNAM users have exceeded an astonishing cumulative number of over 1,350 from 102 different universities and 91 different companies. Finally, to highlight the quality of research work at UNAM, as a testimony to our direction of excellence, out of over 1,200 UNAM address publications, over 220 of them appeared in Nature Index journals, and over 120 of them in journals with impact factors of 10 or above. Thus far, UNAM address publications led to an institutional H index of 77, with a rising citation profile, an average citation of 28 per paper. Altogether, UNAM makes 72% of all publications in Nature Index journals from Turkey, making UNAM #1 as a single entity research institute. For this entire operation, Along with R&D projects, UNAM covers the operational cost and investment needs of its buildings and labs, thanks to a special and unique large-scale support program of law number 6550, the research infrastructure support UNAM has been awarded, which we are very grateful to acknowledge. Under this law, today UNAM is governed by an independent governance board consisting of board members both from and outside Bilkent, and a subset of these members on the UNAM executive board. UNAM now also have a professional manager, our facility manager, serving as UNAM Associate Director, Özgür Yıldırım, who is with us today, Özgür, to provide professional, systematic, and continuous top-notch management of UNAM as a national lab. All of these, where UNAM has come from and where UNAM is heading to, have been possible indeed with all partners on campus and outside, actually even going beyond the borders of Bilkent, working closely with our friends and colleagues all around us and extending all around the globe. Many of my colleagues here have very strong bonds and closely connected with the greatest international institutes worldwide, like mine with NTU Singapore, which I'm also very pleased to acknowledge. This level of connectedness and holistic operation and partnership of UNAM, in my view, grants the whole UNAM enterprise a critical role and a leadership position as a national lab in the research landscape of this country and the region. Finally, before completing my talk, as a final note, I would like to take you to the very basics of a research center. So I will now ask you to close your eyes and imagine on a sunny day like today, a campus with all open labs. Well, this is exactly what UNAM offers on this campus. UNAM provides world-class open labs, truly open labs at the core facilities we have across UNAM, and openly shares them with the Bilkent community and across the country. As you can imagine, this is a huge, huge operation, very costly in terms of the budget and effort, which is made possible thanks to our professional, technical, and support teams, as well as the management, governance at UNAM. UNAM not only provides infrastructure and instrument parks, but also trains our young researchers and students in the state-of-the-art labs and facilities we have at UNAM. In my opinion, this is a great, great opportunity, potentially a major facilitator for R&D success, waiting for all potential partners that are willing to take, which many would say uncommon on a campus like ours in this country. Therefore, I think we should all be very proud to be part of this open lab, open science community and share these values of ours. So we should work all together to embrace this unique opportunity. The last but not the least, I would like to extend my deepest thanks to our very distinguished speakers, colleagues, guests, who have traveled all the way from the United States, Europe, Istanbul, many different parts of the world, and Turkey, to celebrate this special event with us. I would also like to take this opportunity to thank all UNAM teams and offices behind the scenes making this event today possible. For their dedication and their ownership of UNAM, my heart especially goes to the entire UNAM administrative office and all faculty and student volunteers who left this building at 12:30 after midnight to make sure we have a smooth event today. And of course, finally, my thanks to you all for your kind participation and being part of the NanoDay. Please now sit back and enjoy the talks. Thank you. Now, following the welcoming messages, I would like to invite President Atalar of Bilkent University to formally open the NanoDay Symposium to share with us the interesting story of Bilkent University.
Good morning. Thank you for being at Bilkent on this important day, 21st of March. I find this day very interesting because that day unites the whole world on a common thing in which all over the world today, days and nights are all 12 hours, all over the world. something common that we share. 21st of March. Yes. Did I say something else? Today, yeah. So today, I'd like to share you the story of Bilkent University, a little bit of history, where the Bilkent University name comes from, how it's founded, and so on. As you know, Bilkent is a non-profit private university, founded in 1984. And I'll start with the life of our founder, İhsan Doğramacı. He was born in Erbil, now in northern Iraq, but at the time of its birth, it was part of Ottoman Empire. He was first child of an influential Turkmen family in Erbil. He started school in Erbil. At the time, medium of instruction was Turkish, but when Iraq was left, Erbil was left outside borders of Turkey, Turkish was banned from school in 1924 when he was going to school. His father was rich, so he sent him to prep school of American University of Beirut. There he learned English, and that's probably why in Bilkent all courses are in English. He learned Arabic, Persian, other languages, and languages other than English are also important at Bilkent. So we have an international community at Bilkent. He studied medicine at University of Baghdad first, but then he transferred to Istanbul University in his fourth year as a foreign student, because he was an Iraqi citizen at the time. And he graduated as the valedictorian of the Istanbul University faculty. He worked with pediatrics professor Albert Eckstein, who had fled Nazi Germany to Ankara in 1930s. And that's why he became a pediatrician. And because of him, he also learned German. He was gifted in learning languages. He married Aysar, daughter of Hikmet Süleyman, who was the prime minister of Iraq in 1930s. And Aysar Doğramacı was also the niece of Mahmud Şevket Pasha, a well-known Ottoman Grand Vizier of Ottoman Empire. So both sides of the family were, they were rich. Because that's important for Bilkent. He was a valedictorian of the university he graduated at Istanbul. He got a scholarship, and he went to Harvard, Boston. He saw the importance of non-profit private universities, which didn't exist at the time in Europe. So he learned about it, and that's probably why Bilkent is the non-profit private university, the first non-profit private university of Turkey. And he found, after his return from America, right after the war, he decided to emigrate to Turkey with his family because of his family's Turkish origins. So, and then he settled in Ankara because of Albert Eckstein. Because Albert Eckstein was serving in Ankara at Numino Hospital at the time. So he said, I will settle and work with my ex-mentor. So that's why Bilkent is in Ankara, because of Albert Eckstein. And then he had long-term plans. In 1960s and 70s, he found a location in Ankara with water supplies, and he bought the land from villagers in 1970s, the land where the Bilkent is now. And he first constructed the Bilkent Lake for water supply, for trees to be planted, and he planted the trees first, started drip feeding them, the trees that you see were planted in late 70s. And also, he started companies to be able to fund the university that he had his plans for. At the time, Turkish constitution didn't allow private universities, whether profit or non-profit. That was the only universities at the time was state universities. But he convinced the lawmakers in 1982 Constitution. There's a clause which he wrote himself, which allows non-profit private universities. And 2 years after that, in 1984, he founded the first such university, Bilkent University. And he coined the name Bilkent. In Turkish, Bil is the root word for knowledge, and Kent in Turkish is city, so Bilkent is the name he coined. And this is we have about 3 square kilometers of land, and right now we are in this region, the main campus of the university. This is the lake he started, and this region is mostly trees. And over there we have the companies that I'll talk about a little bit. Then we have the housing facilities for faculty members and students, dormitories for students on the other side. And then on the east campus, we have prep school of the university for those students who do not have sufficient English to begin the English education. Plus, we have schools. I'll mention them. And then over here, we have a shopping center. Actually, the whole thing is a city. Many of us don't go to city, don't go to Ankara for many weeks because everything is here available. We have an international advisory board, Michael Young from Rockefeller University, 2017 Nobel Prize winner, Bertil Anderson, ex-president of NTU in Singapore, and Jad Cohon, ex-Carnegie Mellon University president. University's endowment consists of companies, actually. This is unique in the world. Actually, the founder donated the ownership of about 20 companies to the university totally. He or his family doesn't own any share of these companies. These 100%, so university owns, this is unique in Turkey and in many parts of the world, that university owns many companies. For example, Tepe Construction, one of the largest construction companies in Turkey, who built the tallest building at the time of one of the largest bank in Istanbul. Last year, Tepe Construction built the first glass factory in Turkmenistan, about 70,000 square meters in Turkmenistan. Endowment consists of other companies. Tepe Home, a furniture company, cement board fabrication factory, printing press, shopping centers. We have 3 shopping centers, one in Istanbul, one in Ankara. And then we have a Tepe Prime. You might know where the Tepe Prime is. We have an energy production company. We have a techno park. We have one of the largest sports clubs in Turkey, the first and largest sports club, Sports International. We have a high-tech companies. This is the first and only semiconductor manufacturing company in Turkey. It manufactures gallium nitride transistors and RFIC production. Very close. It's on campus. Meteksan Savunma is a military electronics company, one of the largest in Turkey. Bilintur is a Bilkent hotel. Some of you know where it is. TAV is the airport operator. You probably went through this company's airports if you arrive to Ankara or to Istanbul. T is us. We're not the sole owner of this company, but we are the founding shareholder of this company. It has currently some 13 airports, not only in Turkey but around the world. It's operating, so it's a big company. Bilkent is 12,000 students, has 12,000 students, 9 faculties: engineering, science, management, economics, social sciences, law, music, architecture, humanities, education. And we have also schools. Bliss is currently the most popular school in Ankara. It has an international baccalaureate education, and these 2 schools are basically built for the faculty members, kids of the faculty members. International, it's an international school. The director is an American, and when I want to hire some faculty members, if they have kids, I take them to the school first. And when they see the school, they say, oh, this is better than the school in our neighborhood. Anyway, it's a good school. The Bilkent was first in many respects. The first email of Turkey arrived at Bilkent, 1986. First PC lab of Turkey was at Bilkent. First Unix workstations of Turkey was at Bilkent. First web page was of Bilkent. And for a while, for a couple of years, we were the Google of Turkey. Many of our faculty members have PhDs from North America, Europe. 77% PhDs from abroad. And this is in the order of appearance. Like 12 faculty members have University of California PhDs. 11 faculty members have Stanford PhDs, and so on. This is a long list, of course. 1/4 of our faculty are international. This is the highest proportion in Turkey. From 42 different countries. We don't look at passports, just like in the United States. We don't look at passports when we make appointments to administrative positions. We have non-Turkish school directors, department chairs, etc. We had a Greek department chair who was the department chair of international relations. Music is an important part of our music. Music is an important part of Bilkent's life. Every week, except in summer, we have concerts. We have a 700 seat capacity concert hall. We have a professional symphony orchestra, not a student symphony orchestra. All musicians are actually full-time teachers at the Faculty of Music. About 40 concerts are given every year. We have also a 4,000 seat capacity Odeon, where we have in summer big concerts. Alumni, 82% of the alumni are in Turkey. 8% of our alumni is in United States. This is again the highest proportion in Turkey. They are located in New York, San Francisco, Boston, Seattle areas. Interestingly, the next number is in Netherlands. The reason is we have a lot of exchange agreements with universities in Netherlands, followed by UK, Germany, Canada. Currently, among Bilkent graduates, we have 21 professors, tenured professors at US universities. Boston College has 2, Carnegie Mellon has, I think it's risen to 3 now. Duke, Georgia Tech, Ohio State, Texas A&M, UC Berkeley, UCLA, Dartmouth, University, Florida, Gainesville, etc. 34 associate professors, 70 assistant professors, Bilkent graduates in US. For example, one of our graduates, Duygu Kuzum, Bilkent BS, Stanford PhD, in MIT Technology Reviews, this is a magazine, cover page. She was selected among the 35 innovators under 35. One of our very important contributions to the world science is from Erdal Arıkan of Electrical Engineering Department. He was awarded 2013 Baker Award, 2018 Hamming Award, and 2019 Shannon Award. These are given to one person every year. And if you see the list of people who have who have taken these awards earlier, you can see the position of Erdal Arıkan. With this paper, channel polarization, this is currently the 5G's core coding mechanism. And Hawaii uses his method, and it is in 5G standard. And so this is an important person for 5G. Thank you for listening to me.
Thank you very much, Professor Atalar. Our president might be with us for a little while, so if you do have any questions about the Republic of Bilkent, please try to find him during the breaks. Now I will be proceeding with our first invited speaker, Monica Olvera de la Cruz. You can come up, I guess, yes. Sure. So while we are setting up Then she joined Northwestern University in 1986, where she is the Lawyer Taylor Professor of Material Science and Engineering, Professor of Chemistry, of Physics and Astronomy, and of Chemical and Biological Engineering. She is also the Director of the Center for Computation and Theory of Soft Materials. She is a member of the National Academy of Sciences, the American Academy of Arts and Sciences, and a Fellow of the American Physical Society. She was awarded numerous awards and is currently a senior editor for ACS Central Science. She has developed theoretical models to determine the thermodynamics, statistics, and dynamics of macromolecules in complex environments, including multi-component solutions of heterogeneous synthetic and biological molecules and molecular electrolytes. And please join me welcoming Monica.
I think I will need this is not yet connected.
That is not connected. Let me switch this.
Yeah.
That will
And I don't know if I don't know if I need a microphone. Anyway, I want to say thank you very much for the kind invitation, and I am very, very impressed with both the university and the institute.
Excuse me.
Why do I have this?
Pockets.
Yeah. I have pockets here.
Here.
No, I'm just worried that this is, I have something strange here. Okay, that's it. And then this is just pointer, I guess, because I'm not connected to the. Oh, yes, it is. Okay.
Yeah, I just connected that one.
Yeah, thank you. Well, at Northwestern, we also have an Institute of Nanotechnology, and having all of these open facilities, has been what makes us grow in material science and nanotechnology too. So, congratulations, because you're doing a great job. So I'm going to talk about molecular electrolytes. And first I'm going to say this is my group. And I don't have a current picture, but most of them are gone now. And one of them is Aykut, which I think he was traveling to Turkey that day. So that's why I always put him on the side like that. And the group works in soft matter physics. And soft materials are actually basic components of all these living systems, and are integrated now in society in all of our products, but they will play a much bigger role in future devices, because they are reconfigurable. And there are some examples here, like polymers, can change shapes and so on, and then also membranes, they can be elastic or liquid, gels, viruses, fibers, ionic liquids, liquid crystallines, chromosomes, skins, tissue. They are all these parts of soft matter. So this is an example here of a gel, for example. And a gel that is charged, because the backbone is charged, will absorb a lot of water because it needs to cancel the charge. But if you change the environment, you can also collapse it orders of magnitude. So you can change from 600% down. And so all of this sort of like reconfigurability that they have make them very attractive. I'm going to talk about how to design molecules that are molecular electrolytes for specific functions. And I'm going to discuss first these ionic polymers that are composed of different groups that are polar and non-polar, and they form some structure, nanostructures. They are of the length scale of the size of the molecules, and these can be like 50 nanometers or so. So the patterns are of the length scale. Then I'm going to talk, some of the techniques to recover rare earths, which is rare extractions by amphiphiles too, similar amphiphiles, but just of different sizes. And polymers also are used now for concentrated enzymes that make membranes that resemble what is called membraneless organelles in living cells, and I'll tell you that story. And when you have organelles that are with membranes, they are just generally facet and crystalline. And so the physics of this is something that we have been interested in studying. This is a typical example of the nanotechnology and relation of nanoscience. So these are viruses, and the people know that it's a cartoon, but when the viruses are growing, instead of a spherical, they go and become buccal into an icosahedra. And icosahedra is a very ubiquitous shape, as it's a platonic solid that has 12 vertices and 20 faces. And it's very ubiquitous because if something is going to become crystalline, it takes a shape most similar to a sphere, which is the one that is liquid, right, a container. But when it's crystalline, it has many theorems that determine the shape. And one of the theorems, for example, is that if you want to form something that is crystalline, you want to wrap, say, a soccer ball, you have to spike it with buckle, right? Unless the structure has defects. And these defects are points where instead of having a particle, all the neighbors, it has 5 neighbors that are pentagons. But these defects hate each other. So if you take a sphere and the defects hate each other, they are in an inscribed icosahedra because they are in the 12 vertices. And so when the sphere grows, these defects cause a lot of strain. So eventually you have to release it. And when you release it, simultaneously all these buccal points come out and the shape comes. What happened? I can see it here. Okay. So what we do, it's weak. So what we do with electrostatics is, this occurs in the viruses and in fullerenes and also in cationic and ionic lipids that we make mixtures of them, and they form the same structure. So this is like physics, there is these theorems that determine these shapes. Some of the surprises we do is like if you want to make at the nanoscale similar shapes that icosahedra, you can do it with electrostatics too. Here's an example. But what happened there is that you can generate more diverse shapes. And the shapes that you get are the ones that are taken by these organelles that are called carboxysomes. These are bacterial microcompartments. In the cell, there's a lot of microcompartments, crystallines, where enzymatic activities happen because you have to concentrate the materials. Things that find in 3 dimensions is very hard to find each other. Instead, if you have sort of a shell, and this example is the one, is an enzyme that is at the beginning of the fixation of carbon fixations, because they are called carboxysomes. And so, during many years, the people didn't understand the shapes of these polyhedra. And you can explain it with mechanics and very simple physics. Instead of, if you have many proteins forming an organism, a shell, and then instead of buckling, releasing the strain, you can actually take the one that is more easy to bend protein, the more flexible one. Proteins sometimes have some little arms that hang around and they can bend. They're organized to sort of buckle and change the shape to release the strain by making the easy to bend. So that's why you get these shapes that resemble the ones of the carboxyls. And you can make them in the lab also with cationic and ionic lipids and making all of these polyhedra shapes. So this is an example where you use electrostatics to design structures. Where I'm going to concentrate on more functional ones for applications. And these are polymer electrolytes. Polymer electrolytes are now, in batteries, in fuel cells, and they also are very, they are deformable. For example, here it is a gel where I told you before you sort of enlarge the size to make the ions inside electroneutral the system, so it sucks ions, and the ions wants to be freed the water, so that's why it makes the volume very large. Like a diapers, right? They expand, absorbing a lot of water. But if you compress them, then you actually can decrease a lot of energy. So you can storage energy that you can convert with this. And this is a cute paper. That was a cover article in ACM Macular. So Acute is here now, a professor, and was my postdoc. So I'm very happy to see him here. So the other examples are these, what is called ionic cables. An ionic cable is just an electrolyte gel, like that one, and then a rubber band, like a rubber band for your hair, connected to another electrolyte. And then you gate it. And so when you gate it, instead of having a capacitance like a normal, capacitors, solid state, where you put a potential gate, so all of the electrons displaced from the cores, here is the double layer that is moving and absorbing to the interface. So you get a very, very large capacitance, and so in these ones, you can connect cables and play music, for example, and stretch them for orders of magnitude, and the music continue playing and so on. They have very huge capacity and propagation of signals. So this is just to tell you that you can make almost everything devices. They're slower, of course, but they can storage more energy and so on. So I'm going to talk about the science of the polymer electrolytes. So there are two types: the dry ones that are not with water. These are called ionomers. And ionomers generally, because they are in organic solvents that are very low, they generally have very few charges only in the backbone. And you can blend them with other ones that are non-polar. But if they are dry, they actually, I'm going to show you, they form very interesting structures and science. And some of the examples will be Nephion, or also these lamellar of nanostructures formed with polystyrene, sulfonate, and PO. And they are very interesting commercially, because instead of being like the normal electrolyte, so heavy or bulky, expensive, and especially combustible, they can explode, for example, in lithium, because the gas phase, they evaporate. But the polymer electrolytes do not. And they are flexible, low cost, and they are non-volatile. And this is because polymers, when they are in a dense state, they are very long and then tangled with each other, so it's very difficult to form a gas phase. They have a cohesive energy in the structure, even though there are soft bonds, between the neighbors, and only strong bonds are on the backbone. They still have a very large cohesive energy to form gas phases. So let me see. I'm going to tell you about the design, how the people design, or we design ionomers for these applications. I'm not going to talk about a very interesting part, which is dynamics, but just thermodynamics, to cover something a little bit more in depth about these systems instead of just the story. But there are many parameters, and this is one of the reasons why molecular electrolytes are very attractive for devices, because you can change the chemistry, you can change orders of magnitude things happening depending how you change molecular weights or architecture of them. So the parameters that determine the structure of these ionomers are something that we call this is the interaction parameter between them, the length, the concentration of them, the electric constant of the medium, the fraction of charge, sizes. You can vary all of these parameters. So here's the example of a charge neutral block copolymer. So you chemically can link a polymer that has few charges with one that is immiscible to it, or miscible, it doesn't matter. What happens is when you put charges, you change completely the physics. And the way you have to approach this problem is very complicated because polymers can be very long, but the ions are very small. So the techniques we have to approach them, you have to be multi-scale. You have to be able to mix length scales to describe the ions. And why it's important to describe the ions, I'm going to show you because they actually bind with the opposite charges and they form clusters and they form structures inside the medium. If you have no charge, it's known that these block copolymers will form periodic structures, okay? Lamellar or hexagonal cylinders or other micelles in a bulk. When you charge them, they know that they are more incompatible. And so, as I said, it's because you have forming these clusters that bring the things together and they form the structure. And so the first thing that you notice when you add charge is not only that they become more immiscible, but these clusters, which this is the only equations I have, just to understand what is the parameters here. The parameters are when you have low electric constants, for example, relative electric constant of 8, vacuum will be 1, the bare, or a solid system. The important length scale is called the Jerome length, LB, which actually the electrostatic energy between two charges over kVt can be written in terms of the Coulomb energy between a length scale LB over R. So if R is equal to LB, so the distance between them is LB, is equal to KT the energy. So this LB is in organic solvents is like 70 angstrom. So charges that are as far as 70 angstrom apart, they know they have to bind. But when you bring them together and you touch, you have a cohesive energy of them that is called the coupling constant. And that value in water is 1. And that's because LB in water, the electric constant is 80. So you have to get very close the charges to bind, and that's why you dissolve a lot of water, salts in water. But if you go to organic solvents or oils, then this electric constant gets lower, and this coupling constant becomes very large, up to like 33 kT to put apart two charges. And that's why you have very strongly correlated structures. So, as I said before, when you have no charge, you form all these periodic structures, and in the moment you have a charge, I'm going to show you how you change the morphologies strongly. Okay? So, and this is the first thing that happens. You should be familiar with phase diagrams. You know, in material science, we construct a phase space, and in this case, the parameter is the fraction of the A component that has the few charges over the sum of the two. And increasing here, this chi is the length interaction between the monomers, red and blue, over kVt. So if you take the inverse of that, is temperature, if you flip it up. And so here, it will be like high temperature, or very miscible, is one phase. And here is two phase. And the black lines are for the neutral system. If you put few charges, like 15% of charges in one block, then all these lines become like this. And so what it means here is that even going to systems that are compatible, suppose this is polystyrene sulfonate with polystyrene, which is the same monomers. Very few charges, they will phase segregate. They will phase segregate and form nanostructures too. But not only that, but the structures they form are inverted. So what it means is that when you have amphiphiles, they have a general curvature where you will form the minority phase will be when F is the minority, like here, should be this structure, and outside the majority for the packing. But if you have charge, they invert those structures, and they look like if the majority is the discrete phase, and the conducting phase actually is the one that has a charge. So that's actually very interesting for making batteries. And this is an example of how, when you have polystyrene sulfonate, with some charges percentage 25 to 49, you do invert the charges. So it means that the majority component is the one that is dispersed, and the one conducting is the one that has the charges. as I showed you before. This is for coupling constants of 17.1, which is strong. The same phenomenon occurs if you disconnect them and make a blend of them. So every person will tell you, a chemist will tell you, of course, you will have one phase here and two phases of things that have polar and non-polar components because they don't mix, right? So, but the interesting thing is that they don't mix in this area again, we call the chimney, is very similar to this effect. And the structures they form, it's in some regions you enhance the miscibility, even though they are polar and non-polar with respect to the ones without charge, and in some regions you enhance the immiscibility. So it's not trivial effect. And so here is what happened to a blend. Again, when you add the correlations, this is the strongly correlated system, but it's not periodic. So it's not like an ionic crystal, but it's an ionic glass kind of forming with some clustered and connected structures. You form these bridges. And you have a structure similar to what is called eutectics, where you can have here, you can have two phases. This is the charge component. It is the neutral one is here and is with a more concentrated charges. In here you can have three phases coexisting in the same temperature or values. So that tells you the richness of this. We corroborate this by simulations too. So what I showed you before is just a theory with taking into account the structure of the polymer and thermodynamics. But molecular dynamics also gave us that and some regimes are immiscible, and when you increase the concentration, you mix them too. So when you do the block of polymer, it's a little bit more complicated, the mathematics, because you have the same terms on the energies, 3 energies to compute the phase diagram, but then you have to take into account the change configuration, self-consistency. And the change configuration will depend on how much these correlations are developing. But again, we can construct the phase diagrams and explain these. The way we explain it is, we can get the mixing on the different structures and how much concentration is in the different regions of the phase diagram. When we do simulations, the first thing you notice is that indeed when you have a randomly charged system with a block that is neutral, you have these percolated structures forming in the system, very similar to what we find with the theory. And they are connected, and that's, as I say, is very, very interesting for applications in battery. I'm not going to discuss what happens when you put a field and charge, and it's very strongly nonlinear response systems because they're still soft. So if you actually put a voltage between them, they deform the structures and so on. So you have very strong nonlinear response. This is what will happen if you have no block, but just ionomers, a mixture. These systems are what we call random copolymers. So there are an infinite number of components really, because you can have chains that can have the charge in the first one, the second one, or in the middle, and far away. So you have a multi-component system naturally when you do these structures. And these are a lot of richness. I'm going to show you how we're going to use that to construct this second part, encapsulation of proteins. So I'm just going to summarize here. I'll show you how when you have charge, you can change the dye structures very strongly and all the properties and nanophases that they form at the nanoscale. So when you have the other regimes that the polyelectrolytes in solution, and generally they are in aqueous solution, they are polar, and they are very useful also materials. I show you the example of these gels that swell and deswell. But also, you can compact them a lot by putting them with oppositely charged particles, like multivalent particles. And that is used a lot in, for example, packing of DNA. DNA is very strongly charged, but if you put DNA with, say, 3-valent or 4-valency particles of polyamines, it can precipitate. And it takes very dense structures, like, for example, because it's very semi-flexible, if you have gone to your house and you're going to pack a hose, you get a toroid, right? You cannot make a sphere. So depending on the flexibility, you can actually compact them into ionic structures, glassy or more ordered toroids. And so these double-stranded toroids, here is inside a virus. When it's inside the virus, you also have to pack it because it's encapsulated. And if you change the outside compositions of, say, charged particles, you can actually affect the conformation of the inside. So there is some communication between the outside and inside. And that is only due to what is called surface polarization. For the people that is not used to these systems, when you have charges, you have interactions Coulomb between them. And if you have a heterogeneity surface, the interaction between them will depend on the polarization is induced, because the electric fields the charge generates go through the 3 dimensions always, but they change magnitude when they go to different media. So that is called surface polarization effects. And that's very important, because they have, this is some of the reasons also with some of these devices work, because of the polarization, the surface polarization that develops in these systems, the charges. So I'm going to show you some sort of physics of some examples related to that. So the first example is an application to use, now I'm going to combine the random polymers that I showed you before with that are now in an interface between water and oil. I'm going to try to use them in both media, organic solvents and in water. The polar part would like to be soluble in water, but the other parts that are hydrophobic, the more carbon, that would like to go in the oil phase, right? So this is going to be used to make these encapsulate enzymes that are, I want them to be enzymatically active. And so I'm going to show you this. We managed to do it, and we published last year in Science with my colleague, my friend, our collaborator, Ting Shu, that is from Berkeley. So let me just, so why do we want to do that? So generally in a cell, there's a lot of phase-segregated structures. And many of the proteins, like 40% or something like that, are unstructured proteins. There are proteins that look like linear. They are not enzymatically shaped. Those proteins have a lot of randomness on them. So that's why they cannot form this sort of shapes like, beta sheets and so on that enzymes have. So these, we want to mimic that's happening in the cell. But I'm going to try to make them outside the cell and functional. So I want the enzyme, which is the one that is folded, to be covered and protected by some polymer, and try to make it a soft coat so that it doesn't kill the enzymatic activity of them. So examples of these that are relevant is, for example, cytochrome P450, which is an enzyme that 75% of the drugs are metabolized by this enzyme. It's a very important one. And it functions better in organic solvents than in water. Another one is the enzyme organophosphorus hydrolase. This one decomposes chemical warfare agents like serine and pesticides. And again, it's also the components, the products that because are not water soluble. So if you have them in water, they will not be able to function. And the other ones are PET ACEs that decompose polyethylene terephthalate, which are the plastic bottles of 1 liter, the big ones that consumes a lot in the U.S. And this, they compose it into the organic solvents that are made of polymer. So these are important examples of that you want to put outside and use for these other applications. And so this is what we did in the case of organophosphorus. And this is a mat made already. When you put these in organic solvents, you can cross-link and make mats and materials that are functional and sort of actually producing chemicals or decomposing chemicals. So that's what the one we did for the science paper. I'm going to just tell you about the physics of this. How do you mimic these intrinsically disordered proteins? I told you a little bit of an example how it works, but I'm going to show you how the principles, how we're using them outside the cell. And so the key things is that it has to be protected by a little layer of water around these enzymes when you cover it by the polymer. And so we designed these random polymers to do this function. Here is the case where it's known that the activation energy of some enzyme, the enzymes reduce the activation energy, and that it can be strongly reduce the barriers when you are in organic solvents. But the interesting thing is that the organelles that are called the membranous organelles that had been discovered recently in the cell. So in the cell, these unstructured proteins parts concentrate different enzymes. And so when they form, they are spatiotemporal. They don't need to have a shell like the ones of the carboxysomes. But they are enzymatically centers that make fast reactions because they concentrate enzymes. And what's interesting is that the people who work on them says that the medium they are looks more like organic solvent. And it looks more like organic solvent because some enzymes are chopping RNA, DNA, so it's a lot of small molecules that are more organic and it's very concentrated. So, you know, it's a very efficient way to accelerate the reaction. So this is actually exactly what we want to mimic outside, and we have been able to in some cases already. So many people have tried to put these enzymes outside in organic solvents, but when they do is they use surfactants that cover them a lot, so they don't function very well. And so here the key things is, in our case, is to use the normal heterogeneities that are in the surface of the enzymes. So generally, when you make maps of how the structure of enzyme is, you have regions that are hydrophobic and hydrophilic. And the distance between them, I'm sorry you cannot see here, but this is like 2.5 nanometers. And so we're going to use the map of the surface of the enzymes to design the polymers and concentration that will work. But the clever things of using random polymers is that, and I'm going to show you, is that you don't need to actually make a particular synthesis of a random polymer that will be very expensive, right? That will match and help to protect the protein. And this is what people do in drug delivery and so on. They try to build, specific polymers to cover the particular map of charges that they are in the surface. But what a random copolymer does, as I told you in the beginning, is an infinite number of them, right? Chains of different compositions. Not infinite, but a very large number. And so you have a population of chains. Some chains have different fractions because it's random of the other one. So you can do very simple chemistry and generate the structure. And I'm going to show you how you can just call it hydrophobic and hydrophilic, the ones that have charge or they like polar versus the ones that don't, and make the map on the surface of the different proteins we want to encapsulate. And this is an example of, I think it's PTase of cytochrome 450. And so we did a lot of them already. So when you do a map, now you can just call them hydrophobic, hydrophilic domains. And you put a two-dimensional map of the regions where they are hydrophobic and hydrophilic of your different enzymes. And these are the polymers that we have. We designed them to have a little bit branchiness because many enzymes, many unstructured proteins have side groups, amino acids. And so basically it allows them to find and the structures and be reaching the domains they want to reach. So this is just experimental demonstration that when you use these random polymers, you have activity over a long time in toluene. So, and here is the more of the structure I showed you in the beginning of the enzyme covered by the polymer with the polar and non-polar groups. So why does it work? This is a full atom simulation. So it works because we know that when you have the structure, there is a small layer of water, and you can see how the hydrophilic groups are close to this area on the enzyme, and the hydrophobic are outside, and there is toluene there. And this is, you can count how many of the interactions you have that are favorable or not when you throw them you're throwing them in a solution that has all of these polymers, right? So you have to count how they are selective, the different types. And so here I show you what happened with it. You make the map and you can superpose whether you have hydrophobic or hydrophilic groups on the top of the protein. And this is what you count. What I find interesting is that when you make, this is the protein substrate, that you have the hydrophobic, hydrophilic, and here's the polymer, right, that has the hydrophobic and hydrophilic. And so, of course, these ones are matched a lot with the ones on the protein, and then you have some other contacts also. This is the majority of the energy, but what I find interesting is that the local concentration here is that 70% of the groups are close to the surface of the polymer that have hydrophobic, hydrophilic groups, and 30% are the hydrophobic. Well, if you look at the bulk composition, it's very different. So what it means is that the protein is selecting from this batch which one is the better coat it can have. So there is just, you don't have to do any science. You know, it's just self-assembling like that, not natural. And so there's a lot of questions that we ask for optimizing this, and you have to tell me about the time, how much time, because we started a little bit late, but I don't want to. 10 more minutes? Okay. So let me summarize what we know by the full atom, is that it's always a shell around of water, and that the proteins is selecting these favorable ones. But you cannot do a lot of proteins this way, you know. Neither you can look at other questions like what happens if you change the composition. This is a random composition of polymers where you have chains that can have only 1% of hydrophobicity up to 80% and so on. So it's a composition of the, actually the charge, this is the one that has charge. So you see you have chains with many different fractions of charge, and there's a mean composition. So you can vary this batch by changing the compositions in the beginning of your polymerization. You can say I'm going to have only 30% or 40% of the other one. And so that gives you a different belt for the proteins to choose from. And so the coarse grain models is very simple now. You can just make, you know, coarse grain the size on the bits outside and the polymer, and you choose ones that are intolerant. Basically, the ones that have the carbons are now in good solvent. They actually want to solubilize in toluene. So the ones that are the poor solvent, attractive, are the ones that have polar. And so you only have the parameters to play with, which is the degree of self-repulsion of the ones of the water with respect to the attraction to the protein. So you have these parameters, very few parameters to play with to understand how to cover this. In the coarse grain model, it allows you to find, you know, will be the degree of absorption as a function of these parameters. And you can see that, you know, there are sometimes maximum. If you start increasing too much the attraction between the polar groups on the polymer, then of course you start not covering much the protein. And so, you know, we are able to quantify now the degree of encapsulation as a function of these parameters and as a function of how you change the distribution of the random copolymer degree of hydrophobicity. So the interesting thing is what you can also quantify how much is what I call sequence, the selectivity sequence. If you make a bunch, this is the selectivity equal, so 100% identical. And when we take another batch, you want to ask yourself, is the protein choosing the same sequence? And they do, actually, because the random one will be 0.5, but they are all higher than that. And so you can actually calculate that degree of selectivity for the encapsulation as a function of the parameters on your model. So this is something that we do what we call multi-scale. We started with something that was full atom, then we go to coarse grain to make sort of larger and larger structures and association. And indeed, you can now get what is the initial conformation of chains, and the ones that you are left, that are absorbed, are the ones that have more percentage of the I say in the beginning of the hydrophilic ones, which is a fraction of the charged ones. So you can see the distribution that is close to the surface. And just to show you, I mean, other design things you can do is like which ones are actually able to be dispersed in this way, which type of proteins. And so what you can do is to calculate how random is the patches in the surface of the protein. So if the protein is very Janus, for example, so the distance between the points are very spread, very large, then it's much more difficult to cover it. But if they are very random, like the 2 nanometers one, a very random plus minus hydrophobic, hydrophilic, then those ones has very peak distributions. They are much easier to actually solubilize with these methods in toluene. So this also shows that it's very versatile. We can change the compositions, the values, and we have done many proteins. Now you ask yourself, so what? What did you achieve with that? Well, we actually have a summary of this coarse grain now is that we were able to, quantify this selectivity of the protein and what are the parameters that make it more or less selective and so on. There are many questions, And some of the questions that remain is, the proteins that are difficult to extract in water. I was a little bit cheating because I told you that I have a layer of water and oil. The process is done in a it's in a different way. If you try to do it in water, you cover very little of the proteins. So what we do is you dry them. You first dry them, and then what it becomes a very concentrated ionomers now, which is the first part I talked to you about, these channels of these ions. So basically, this is what happened in the actual process when you start. Oh, it doesn't play. When you dry them, then the organic solvent, the concentration, the electric constant of the bulk where you're drying around the proteins, you get a layer, but the outside is forming these ionic clusters. And these ionic clusters then are put in the toluene, and then they open up more. And so you can actually cross-link them and membranes or something like that. Some of the new physics is we can understand why it's very hard to cover them in water when they are polar, when they have a lot of polar domains. And this is because the water orders a lot around the charges. And this is something very surprising for us because, people know that, the water has the dipole of the hydrogens and the oxygens. But to order water is very difficult, right? So in order to have, say, a surface where the positives and negatives, the water is doing that, it will be very costly. But nevertheless, it's actually very organized. And this is something that we found. For example, when we go and calculate for how long a distance superposing the water, the dipole is actually persistent. In the case of the oxygen, up to 16 angstroms away. And in the case of the nitrogen, plus in less. But it's a very, very organized shell. And in those cases, the electric constant there is much lower because it's very ordered. The polarizability, the electric constant of the water in the bulk depends on how much the fields are orienting these things fast enough and so on when the charges move. So that's why it's very hard to do it. What we're going to, and I told you in the beginning, is to extract them from the water using some random polymers charged, but with some perhaps tails or less tails that are in the oil. And these will allow the proteins, the structure here when the charged ones solubilize. If you don't have hydrophobicity, it goes to the water. So you have to be very careful of how much percentage of hydrophobic in the oil you have. And these structures are very organized in the surface. So the idea is that you are designing these sequences to attract certain proteins because you already know which sequence of charge and hydrophobic are actually working. And then the idea is to move them to the oil. And that's called a technique, this technique is called solvent extraction. And it occurs to extract rare earths, I told you in the beginning, with amphiphasts. So the way it works in rare earths is that you design amphiphasts that go to the interface of oil and water, and they selectively pick up the actual size of the rare earth, the lanthanum, that they can vary but very little in size, but it's very selective. And then it brings them to and encapsulate them and bring them to the oil. This is called solvent extraction. And it was used to clean all of these nuclear waste. Cesium is very reactive and remains reactive for 100 years, something like that. So in the US, they're very proud now with the 40 years of the Department of Energy that they were able to clean a lot of the cesium by this technique. So it's very well known in this area of cleaning nuclear waste and recovering rare earths. So we're trying to get it to work in our systems. So I said I have some physics to show you. And so I start saying that polarization was very important. For this case, it's very simple to see that once you clean them in the oil, these tails are carbons supposed to be solubilized in the oil. So this is something that people do to solubilize colloids. They put chains that are in good solvent and they don't collide and agglomerate. But they do, actually. They form aggregates in the oil too. And so the physics of this is very interesting. So here is a coarse grain model. In the beginning, you didn't see it. It's I put 3+ charges. Let's see. Here, this is 3+ charges. This is a 3+. It's neutralized with negatively charged. And it's a droplet of water in oil, okay? So you can see that what the surface polarization is something that is called the immense charge, people call it. If you take a medium water that has higher electric constant to a lower one, it's repelled. And it makes a charge, fictitious charge, that is of the same sign of the particle. So it develops a charge extra that repels the particles, but that actually correlates them more than if the opposite case. The opposite case will be if you have a droplet of oil. Suppose you have an enzyme, and outside you are putting, so this is the oil, and outside is in water. In that case, the interactions are going to be depleted because the immense charge is of opposite sign, so it cancels the interaction between them. The interaction between these droplets is, this is the map. You can separate the charge with the induced charge. That is called the surface polarization. When you do that, this is the result. The real charge, if they were without the dielectric polarization, is this charge to charge. But when you put the induced charge of the surface with the real charge, then you get these attractions. This is 1 over r to the 6 because it's dipole-dipole, they're moving. So it's very, very strong. And if you are in water, the interaction is 0 because actually the interaction between the charges is canceled with the induced charge. So this is something very interesting. I told you in the beginning, viruses generally are covered by a membrane that has a very low dielectric constant, and it communicates to it. And it's very strongly correlated, the charge, on how the distribution of the conformation of the inside. And so this can be explained with physics. The reality is that these droplets have very concentrated salt. So really the dielectric constant, even in bulk of water, when you add a lot of salt, it decreases a lot. It's not 80, but it's 40. And so I'm going to show you an example of what happens if you put inside the lower electric constant and inside a droplet with a polymer that can adjust its conformation. And so you calculate the energy of confining it to this dielectric. It's the electric confinement, kind of. So in the system, how does it push inside the electrolyte? And you can see, depending on the size of the spherical virus, where you put, say, the RNA or somewhat more flexible, how is the minimal size is affected by the confinement. But what is most interesting to me, and as I'm going to end here, is that if you don't put polarization, surface polarization effects in the coarse grain models, then it just, it just changes conformation and varies very, very little. Even when you have different electric constant, if you have polarization, it doesn't affect very much the conformation. If you start putting charges around that absorb to this outside medium, but if you actually put the polarization, you can change the conformation to make, say, for example, like a cross, like that. And this is because you are deforming the structure, and you can, and I showed you in the beginning, viruses, they seem to be able to communicate and change the shape of the inside container. So I hope I have persuaded you that with very simple physical models, you can explain some of the things that you observe. I'm going to show, say, I didn't show all of the examples we work on, of course, but this is just sort of like a summary of the things that I very briefly went through it. Encapsulation and so my cells and phase dampers. And with that, I'm going to thank you for your attention.
Thank you very much, Monica. Now we can accommodate some questions. Yes, please, Urartu.
Thanks for the nice talk. I have questions regarding your polymer protein systems. The first question is, when you just put your protein, like there's all those polymers as cakes for proteins, so one of the concerns, if it's an enzyme, it's most likely that there will be some blocking of the active site, because active sites are containing a lot of charge residues or aromatic residues in there. So
that's why this works, because it's very soft. The randomness, because you put in a random polymer that can have this sort of these side groups, is very soft, the coating. So it allows a lot of access to it.
Following this, my question is going to be like, because these are interacting and just when you change the code, actually you most probably are going to affect the conformation of the protein as well, and which means that you may get some problems with the conformation at the active site, because residues are really exposed,
Right.
So you may change, like there will be change in the software specificity or the activity of the enzyme. So, I mean, what's your observation about this, or are you doing it protein engineering, or?
No. Protein engineering will be, we do functionalize with other groups. I didn't talk about that. In these cases, we don't really perturb the structure. You have actually to let it breathe, because it's known that when they do enzymatic activity, it's not totally frozen. The active sites are still active. For example, we just did cytochrome P450, one of them, because there's a family of them, and they form dimers. And actually in the dimers, we see that the active site is exposed well, and we had covered that one now, and the same technique. In fact, that one, we didn't even need to put charges on the polymer, just PO with some hydrophobic, but long chains PO, and covers very softly. And so the thing is that that's the whole thing of using these polymers, that are not going to really, suffocate the structure. And they're supposed to be conduct for the products to come in and out. That,
I just want to add one more thing.
Yeah.
So how about, you track this approach adds up the temperature sensitivity of the protein in a positive way, or the proteolysis? So does it also help the work against the proteolysis of the protein, or do you do that? Also, this is not for water system, but
Yeah.
how would you comment on that?
Yeah, we're working always at room temperature, right? And the concentrations, are sort of like.
Did you try
No, it will denature it, I will imagine, yeah. High temperature. I'm not familiar. I'm not a biologist, to be honest, but, it's just polymer physics.
Yeah, maybe
but
finding ways of increasing the temperature of proteins are something that
people want. Okay, so if you stabilize it, we know that the structure, secondary structure and particles are preserved when you cover it, but we haven't looked at what happened with temperature.
Because there are a lot of studies where people are trying to, people like me, trying to insert some IDPs, using the sort of proteins to achieve such things. Because I think that was one of your inspirations.
Yes, it's to really make them more functional. At this point, it's just industrial, right? Actually, the cytochrome P450 is from Frances Arnold, of some of the enzymes, and Exxon got them and wanted them to put them in toluene. So, if there's money, I'll do it. No, it seems to be very interesting possibility. Yeah.
Thank you very much for your very interesting lecture, Monica. I was wondering if you think it is in principle possible to design a copolymer or copolymer protein system that would actually cover a virus of any arbitrary choice specific to the virus.
I think they can do that, yes. I would think so. The virus surfaces are well known, right? And it's more, yes. I haven't.
People use to pass away all the viruses of any system they exist?
I don't know if it's, I would think that it's possible with polymers. The tricky thing here is the molecular weight. For example, if you use very long, it kills glass, it doesn't work. These ones that we work with 80 units only. So they are short, but there are many of them coming together. So there is a trick on the dynamics of the systems and solubilities and so on. But I would think that, if you make a block copolymer, which just a lot of polar groups, it probably will go to the surface of the protein, of the viruses, and cover it. When you use cationic and ionics, they are one tail and they form by layers, just by electrostatics, because the head groups attract the other ones. And so you can design the head groups and so on in a way that you can do flat structures covered in a more open, as I did with the random systems. I would think so. That's why they are so versatile. That's what I said in the beginning. Soft matter has a lot of opportunities. Yeah. Thank you.
So I have a question about this hydrogen bonds near the protein surface. So when you look at the dietary concept, I think you calculate the dietary concept. When you look at the genetic behavior of these hydrogen bonds, typically they're slower near the hydrophobic sites compared to dietary sites. Lifetime.
Oh, yeah, the time. Actually, Yes, Trung is doing it because, you know, it's very fashionable now. So we finish our correlations and somebody else throw another paper, heterogeneities on the surface. So, but now we're doing the time dependent to sort of have something new. And I wanted to see how does it affect, you know, interactions between two proteins. I mean, it's, yes, this one, yeah. I found it very perverse, you know, for the water to do this organization. In graphene is so structured, the dipoles, that I call it as a metamaterial. If you try to explain the interaction of charges, they can actually, opposite charges can repel because the water dipole is stored. So, you know, it's artificial because you're just pushing them there, but the response is like really very dramatic when it's so ordered around certain surfaces. Yeah. The strange things of water. Yeah.
Thanks very much. I'm interested in the last part, the water droplet cycle.
Yeah.
I wonder if this droplet size has any effect on those interaction or not. Do
Yes.
you have interaction those droplets with each other or not?
It does, the size, yes. Because when you have much more things, the whole correlations, the 1 over r to the 6 is due to the dipole-dipole correlations, you know, the fluctuations. Dipole, if you have more, it's more average out, the effect, and it will be less strong, yeah. Yeah. So, yeah, I mean, I don't know if I answered physically correct there. Polarization is very tricky. If you do a capacitor, with or without polarization, you get the same answer, unless you do differential capacitance or you look at special things, you put the charge of a specific values. But if it's, say, neutral, you don't see any difference. It's very close to zero or neutral, the charges on the surface. So, you know, it's not so simple to understand when polarization is important or not. Yeah, it's what we did was the first variational approach. When you do molecular dynamics, you have to have a mass to things. And polarization doesn't have a mass unless you actually make a fictitious charge and make a Lagrangian formulation of it to a sign that is moving at the formable phase. And that has something we did in 2012, and we're starting to use it more to make the formable interfaces and so on. But it's very new, right? Because people do full atom and put the water and everything, so you have the polarization, but you can do very little systems. Now, if you really want to go to see larger scales, you have to do this coarse graining. Fix. Yeah.
All right. And with this, I'll be closing the first session. Let's thank our speaker one more time. I would suggest sticking to our schedule, so let's try to be back at 11:30. Now we do have the coffee break.
I do have a question for you. So you don't have a board of trustees that, yeah, and then there is someone that takes care of the finances, but the finances are so different that our endowment.
Thomas, you want to check the laptop?
Sure. Yeah. Tamam. Ben bir şey yapmıyorum ama. Ha, şu oyun. Gelmiyor mu sesin? Kısık mı ben? Bence şimdi oynat dediler ya, o yüzden. Tamam mı? Sen kendi kameranı mı deneyeceksin yoksa yayını mı deneyeceksin? Yalnız bu sesi kısık bence bunun. Çıkmıyor ki. Ben duymuyorum Ken. Ha? Çok sinirlendi bu beni duydu ya. Vallahi artık böyle falan oldu. Adam şurada bana kes
Birbirimize bakışımız var.
Şu an denediğimiz gibi Duygu sen de konuşabilirsin. Deniyoruz yani mikrofon deneyeceğiz. Sabah da denemiştik.
Efendim? Nasıl? Heyecanlı değiliz. Her şey yolunda. Çok güzel geçiyor. İyi ki geldiniz. Teşekkür ederiz. Se. 1, 2, 3.
Bunu
İyi mi?
keseceğiz değil mi? Canlı yayın mı şimdi?
Bu canlı yayındaysa çok kötü. Bittim. YouTube'u. Bizi izleyen izleyiciler merhaba. Merhaba. Yeter mi?
Yetiyor
Yeter
mu?
mi?
Yetti.
Bence iyi. Teşekkür ederim. İyi şarkı söylüyorum.
Sen açtın mı hepsini? Evet, bu da açık. Ne söyleyeyim? Geliyor mu? Ben duymuyorum kendi sesimi mesela. Sen beni duyuyor musun? Ama şu an duyuluyor mu? Salonda geliyor mu sesim size? Geliyor mu? Biraz önce. Hangisini? Bunu mu deneyeceğiz? Ya bu şöyle duyabiliyor musun bu şekilde? Tamam. Salonda duyuyor. Tamam. Kapat. Hı hı. Orayı kapatırız işte. O bir HDMI kablo.
That's not good.
Just take it a little bit slow.
Sure. In France, we always start 5 to 10 minutes or even more late.
It's not too bad. So that usually we had 4 talks on a single day, but it was then so dense.
Yeah.
We couldn't tolerate any delay. So this setting is perfect.
Yeah. Coffee breaks are a good buffer.
Yeah. So I'll just go over this one that you have provided to us. If there's anything
Sure.
you want to add or change.
No, it's okay.
All right. Can I get your attention, please? Sorry. Energy. Okay. Welcome back. We will be moving on with our second talk. Let me introduce you our next speaker, Mr. Thomas Hermans. He's an assistant professor at the University of Strasbourg and a group leader of the Laboratory of Non-Equilibrium Complex Systems at the Institute of Science and Engineering of Supramolecules since 2013. He studied chemical engineering and chemistry at the Eindhoven University of Technology, followed by a PhD at the Faculty of Biomedical Engineering at the same university under the supervision of Professor Bert Meyer. Next, Dr. Hermans joined the group of Professor Bartosz Grabowski at Northwestern University, whom I guess we have hosted a year ago or so at Bilkent University. And he received the ERC Starting Grant 2017, Theme Chemistry Award 2018, Prix Guy Orson 2019, and he is the coordinator of MSCA Innovative Training Network 2018, CREANet, on chemical reaction networks. He is a co-founder of Q-Fluidics, a company working on ferrofluids and magnetostatic pumping. The main goal of the Hermans lab is obtaining adaptive, self-healing, self-replicating, and ultimately living systems and materials using molecular self-assembly under far from equilibrium conditions. Let's welcome Professor Hermans.
So thank you so much for the invitation and for hosting. Everything was really perfect, perfectly arranged. So today I chose to kind of split my talk into two topics, and they are totally disconnected. So if you fall asleep in the first part, you still have a second chance later. And so Strasbourg is here. It's on the border between France and Germany. It's a very nice city. You should all visit. And so our institute is called ISIS, so it's Supramolecular Science and Engineering. It's not a very good abbreviation at the moment. And but we are the good guys. We are the good guys. And so we have a kind of weird structure of our institute. So we have senior, these are the senior PIs. So we have Jean-Marie Lane, Jean-Pierre Sauvage. Oh, sorry, I forgot to update. So yeah, sorry, I forgot to update his Nobel Prize. Okay, but we have, well, being attacked. Okay, so we have senior labs and we have junior labs. And we work in a very multidisciplinary setting, but around supramolecular systems. So our group works on three main research lines. So we have this research line on chiral separation by flow, but today I will not talk about that. So if you want to know more, you can go to our website. But today I have two topics. So one is dissipative supramolecular systems, and one is a very strange kind of way to do fluidics, which I'm pretty excited about. So the first part, I will talk about out of equilibrium systems. And so what do I mean with out of equilibrium? It depends on who you talk to from which field. So this is a movie actually of a living cell. So it's a fibroblast and it's crawling around. And in this experiment, we accidentally put the laser power way too high and we kill the cells. So what happens is you go from this very complex shape that's moving around to just a round sphere. And actually, this second cell is kind of playing soccer with the dead cell at some point. So you go from this incredibly complex thing to something very boring. And so this very boring thing, well, depending who you talk to, is called thermodynamic equilibrium, right? So when you're out of equilibrium, you have all these chemically fueled processes that give you complex behavior. When you're in equilibrium, you go to the soap bubble. So I just want to put this slide, which I always show, to kind of define this a bit more precisely. So you probably know that the thermodynamic equilibrium is the lowest point in the delta G, so the Gibbs free energy landscape. So this we all know, and you can use normal thermodynamics to describe all these things. Also, chemists have become very good at controlling so-called kinetically trapped states, and these are local minima in the energy landscape. So we call them non-dissipative non-equilibrium states. And so non-dissipative means you do not need any form of energy or matter to keep your state. And non-equilibrium because there's only one thermodynamic equilibrium. So this is quite well understood. So what we are looking at are so-called dissipative non-equilibrium states. And so here, this is not an animation. This is a movie recorded in my office. So this is my whiteboard, and this is aluminum foil, and this is a ping pong ball, and this is a hairdryer. And so the hairdryer is blowing hot air, and it's preventing the ping pong ball from falling down. So the gravity would be delta G in this case, and the air is preventing the system from relaxing to thermodynamic equilibrium. And depending on how hard you put the hairdryer, it can be just kind of floating around there, or it can do more interesting things like, in this case, it's kind of oscillating around. So those are the states we are after in chemical systems. And so one of our biggest inspirations is this. This is again a cell, and you see here in this movie, you see this bright spot here, which is called the centrosome. So the centrosome is where microtubules start, they are nucleated, and then they grow outwards. So schematically, it looks like this. You know, this blue thing is the cell. This is the centrosome. And the microtubules, they grow and they push out against the cell membrane. And where the sum of all forces is 0, it's the center of the cell. So one of our goals is to, eventually replicate this whole system. So we are also working on surface nucleation, which I'm not going to talk about. But today I will focus on this, let's say, trying to make an artificial microtubule. So let's look a little bit closer at the microtubule. So this is a very beautiful animation where you see that these tubes are hollow and they are actually very interesting supramolecular polymers. So they are proteins that are held together by non-covalent interactions. And they are incredibly strong and stiff, so they are stiffer than steel. But in the cell, they are still very dynamic. So the typical time scale of growing and shrinking is like on the order of 1 minute. And this is kind of strange if you think about thermodynamic equilibrium, because normally when we make a synthetic system, which is very strong, very rigid, there's no dynamics. You know, association is very strong, so everything is locked. If you make something very dynamic, it's usually very floppy and very weak. So what does the cell do to get around this? It uses a chemical fuel. In this case, it's guanosine triphosphate over here. And GTP binds to the tubulin monomer, which then it can nucleate and form a microtubule. So we're over here. And then the TP is hydrolyzed to GDP, which then destabilizes the microtubule and it falls apart. So you can have very good mechanical properties and very high dynamics at the same time using this kind of chemically fueled systems. And also very interesting, so in the 80s, Mandelko, he already found that you can get oscillations in microtubule systems, so collective growing and shrinking of microtubules in vitro. And he also showed that you can have waves of polymerization in microtubule systems. So these were things that were an inspiration for us. So one of the first chemical systems that does anything in this direction was by one of our colleagues in the Netherlands, Jan van Esch and Job Boekhoven. And they basically proposed this approach. So you have here a molecule which doesn't self-assemble because it's charged. You do an organic reaction, so you do a methylation, you go to this methyl ester, and this one now self-assembles, but the methyl ester also hydrolyzes back to the acid, so you get disassembly. So you get what's called transient self-assembly. So you start from a liquid here, it forms a gel, and then over time it relaxes back to the liquid. So that's kind of the state of the art in our field at the moment. So before that, you know, many materials are so-called stimuli responsive. So it's you change the pH, you change the temperature or anything, the material responds. Okay. And if you reverse the stimulus, you lower the temperature again, it goes back to its original state. So transient self-assembly is a little bit beyond that, right? So you give a stimulus, let's say here, and you go from state A to state B back to state A. So what we are trying to work on is so-called steady states. So we apply a stimulus continuously and then see how the system reacts as a function of how hard we apply the stimulus. And so one more thing I have to explain to make sense of the different things I will show you is the distance we are from equilibrium. So when you're close to the thermodynamic equilibrium, you have equilibrium-like behavior. If you're very far from equilibrium, you get all kind of interesting things like emergent properties. So what is an emergent property, right? So this is a model for the growth of rabbits. So if you have 2 rabbits and they like each other, then they can reproduce, right? So you go from 2 to 4 to 8 and so on. And this is the equation, right? So the number of rabbits at a certain time t times 2 will be the number of rabbits at the next time points. And if you run this on your computer, you get this population. So it's not a very realistic model because otherwise the whole planet would be covered in rabbits. And it's not. So you need a little bit more sophisticated model, which is this one. So now we introduce this term R, and R times the number of rabbits at time t times 1 minus that depending on the function of r, it gives you either just a kind of boring increase and then a plateau. But if you increase r, you get already oscillations. And this is from this very simple equation. It's not even a differential equation. So you can get oscillations, and if you increase r even more, you get this seemingly random behavior. So if you plot the number of rabbits at the long, some time 100 versus r, you see that below, when r is smaller than 1, all the rabbits die, so it's really sad. And then between 1 and 3, you have one single solution, so the population of rabbits grow and then it stays constant. But then you have this interesting point here, which is called a bifurcation. So when you have a bifurcation, beyond that point, you have enough instabilities to get things like oscillations, waves, and patterns. So this is kind of where we want to go beyond. So I will show you two supramolecular systems. One is in this, let's say, non-equilibrium state, but close to the equilibrium, and one is in a far from equilibrium state. So our general approach is we really like this building block, which is called perylene bisimide. And this bisimide is functionalized with this two arms. Actually, I only draw one, but there are two. And the arm has a peptide and a PEG. And the peptide is recognized by an enzyme called kinase, and kinase takes ATP, and it takes one of the phosphates and it puts it on the serine residue. So here's the serine, okay? So we go from a 2+ charged arm to a 2+ and a 2-. So we go to a Twitter ionic state, which is much less soluble and therefore more assembled. And this process is reversible, so we can take the phosphate back off with another enzyme called phosphatase, which cuts the phosphate off again, and you're back here. So this is now not an equilibrium reaction. It's a chemical reaction cycle, which is driven by a chemical fuel. So this will be important for later. Okay, so first we showed that when you phosphorylate the two arms of the molecule, you get an increase in size. So in solution, we almost double the size of the assemblies. And also in the solid state, we see nice bundles of fibers. But more surprising was that actually the chirality of these assemblies inverts. So supramolecular assemblies, they can, the molecules stack on top of each other. And because the arms are chiral, the whole assembly is chiral. So you make a helix. And this helix, so this is circular dichroism. Basically, this tells you you have a right-handed helix. Then when you phosphorylate, it inverts the chirality. So that was kind of strange, but also good because we can now follow the phosphorylation with spectroscopy. So in a typical reaction, you would take the molecules and the enzyme and you get phosphorylation, then you add the phosphatase and this you dephosphorylate. So this would be the typical stimuli responsive system. You do stimulus A, stimulus B, you go back. So I don't have time to go through all this whole network, but actually when we started working with enzymes, we thought, okay, you buy kinase and you add it and it phosphorylates. But it turns out it's like really complicated because the kinase has 3 binding sites. One where ATP can bind, one where ADP can bind, so this is a, let's say, product inhibition, and one where the peptide can bind. So, okay, let's not worry about that. So this basically, you phosphorylate the molecule, and on the way back, you dephosphorylate. So that's the network. We can put that in a model with a lot of differential equations, but the main result is this. So these are experiments, the dots, and the lines are the model. And this is now this transient self-assembly, right? So we add everything in one flask, we add a shot of the fuel, and we get phosphorylation, right? So you see here, you get phosphorylation, and then you get dephosphorylation. And actually, so these are the 3 states, so it's non-phosphorylated, monophosphorylated, and diphosphorylated. So what happens with this red curve, which is kind of strange here, you get a peak and then a second peak. This is because when you phosphorylate one arm, and then you are monophosphorylated, then you have 2 arms phosphorylated, and then on the way back, you go back to the mono arm. So you pass that species 2 times, giving you 2 bumps in the kinetic curves. Okay, so we understand this. And then we said, okay, we want to go to these steady states, just like what you have in the cell. So we said, okay, let's do a shot of ATP. We get phosphorylation, dephosphorylation. We add again a shot of ATP, but now we get phosphorylation and it doesn't go back. So we found that when you dephosphorylate, you release phosphate, inorganic phosphate in the solution. And if you look in our network, which I went very quickly, but if you look closer, you can see that the waste is phosphate, and actually phosphate is an inhibitor for the phosphatase enzyme. So your system is poisoning itself. So we thought, okay, what can we do to reduce this? And the simple thing is basically what happens in your body. You have kidneys, and they filter stuff out. So we decided to make this flow reactor, which is basically a dialysis cassette. So our entire system is confined in this chamber with two membranes, and only the fuel, so ATP, and the waste, ADP and phosphate, they can exchange, and the rest just stays inside. So now we can keep our system running basically continuously. So I'll walk you through these different steady states. This is a bit hard to follow. So what we do is we have our chamber, and we flow a continuous flow of buffer around with a certain concentration of ATP. So we put 1 millimolar ATP, and we measure the mole fractions of the different species. So this is non-phosphorylated, monophosphorylated, diphosphorylated. So we reach a steady state. Then we increase the concentration of ATP. We go to the more phosphorylated state. Again, we reach a steady state. If you remove the ATP, then the system relaxes to the thermodynamic equilibrium. So you dephosphorylate. You go here. And when you add, again, new fuel, then you go again to a new steady state. So now the composition of your system depends on the kinetics of how hard you drive your reaction cycle, and not on the thermodynamics of your system. So we were very happy, and we submitted. And of course, the reviewer said, well, this is nothing new, because there's something called Le Chatelier's principle. So Le Chatelier had this very vague kind of definition, but chemists really like this, that says that when the system is at equilibrium and you disturb it, it will respond to minimize the effect. Okay, this is a bit vague, but if you look at it in an energy landscape, right? So you have a state here which is high energy, is 100% monomers. Here you have 100% polymers, and we are somewhere in the middle. So we have polymers and monomers in exchange, in equilibrium. And so we are actually not in Le Chatelier's principle, because we have a covalent reaction which makes a different molecule, which is the phosphorylated one, which has different self-assembly kinetics, or kinetics and thermodynamics in this case. So a different energy landscape, and we have these irreversible reactions that go from this molecule to here and then back down. And we don't have a set of coupled equilibria between this. If these would all be equilibria, then it's Le Chatelier's principle. Like you add something here, all the equilibria shift. But I could also understand the reviewer, because it was a non-equilibrium steady state, but boring, let's say. I can also mix these things by hand and I get the same result. So in our second system, we said, okay, let's try to do something better. And actually just a very quick literature thing. So there are people like my former supervisor, Bartosz Rybowski, that have coupled chemical oscillators to materials. But you have the oscillator, which is doing its oscillations, and you have a stimuli responsive material that follows that behavior. So if you link a pH oscillator to, for example, this surfactant that changes from micelles to vesicles with pH, then the system will follow. But what microtubules do is the microtubule is the material and the oscillator in the same system. Okay, so it's quite different. Okay, so we again go with our perylene bis imides, which we really like, but this time we don't play with the tails, but we play with the redox state of the core. So this molecule is very nice and pink, and if you add a reductant, so if you look in the movie, we add the reductant and it goes to very deep purple. So this deep purple is this state. It's a dianion. It has 2 negative charges, and it's disassembled, again, because of charge. So then if you leave this open in air and you stir it, you get oxygen that oxidizes to the radical anion, which is bluish. It's hard to see here. And if you oxidize further, you go back to the neutral state, so you get the pink color back. So this is now nice because we start with a very strongly assembled system in this state. Here we can disassemble, and when we oxidize back, we go to a monomer, but the monomer has a high propensity now again to self-assemble. So we said, okay, let's do this again in these steady states, because this is kind of our thing of our group. And this experiment seemed like really stupid when we started, because we have a reactor and we add a reductant and an oxidant at the same time. So if you're in chemistry or redox chemistry, this is strange, right? Because of course the reductant and the oxidant will immediately react with each other, and even more than with the molecule. But we did it anyway, and we found that still if you add it enough, it still reacts with the molecule. So we did this in a semi-batch reactor, and if you do it exactly at the right conditions, you get something like this. So we found spontaneous oscillations in color between pink and then now it's purple, and then it will go through blue and then back to pink. So this was kind of very exciting to find oscillations, right? There are not so many oscillators out there. So what we did is, this is from nonlinear dynamics, right? So you map the phase space, you change the total concentration, and we change the flow rate of the reductant, so basically the total rate of reduction. And you find indeed this narrow window in the phase space where you get damped oscillations. And if you don't have enough reductant, you have this, again, this boring steady state like what I showed in the first system. Okay. The nice thing about this system is that you have these nice colors, so we can just follow it with a color camera. So this is actually an experiment. This is color space, so X and Y coordinates. I will zoom in here, okay? So it's still, X and Y is still the same, these are colors. So we start in this neutral pink state. We go to the dianion, which is purple, and disassembled. Then we oxidize through this radical anionized blue back to this state here, which is again pink. And then the system starts oscillating and it damps and it ends up somewhere here. So we were very happy because we have separately studied these different states, and we know this is a polymer and we know this is a monomer. And then, of course, we had a reviewer that said, but why don't you show that during your color oscillations, the size also oscillates? So I don't know if you've ever done light scattering, but light scattering in a stirred vial is difficult, and light scattering on anything with a lot of colors is also difficult because your light will be absorbed. So we had to build a near-infrared static light scattering setup, which we did. And then what you can learn from this is actually quite interesting. So in this graph, you have the light scattering intensity. So higher signal means bigger assemblies. And you have color here. So what happens is you go from the pink state to the purple state. The color changes almost immediately. So it takes like 10 seconds. But the scattering intensity then still takes 3 minutes to reduce. So apparently the color changes immediately, but the size does not. And on the way back, so if you go from disassembled to assembled, what we thought initially, so you go from purple to pink, the color changes very rapidly, but then the scattering intensity takes several minutes to go up. So we studied this in a lot of detail, and we came to this picture. So basically the assembly pathway consists of a nucleation and an elongation step. And we know this from doing kinetic experiments. So alpha is the degree of polymerization. 0 means 100% monomer, and 1 means 100% polymer. And you follow this versus time, and you can do this at different concentrations. You can basically fit this with a nucleation, elongation, and fragmentation step. And so if you add seeds, so seeds are preformed polymers. So we take a polymer which is 1 hour old and we add it to the monomers. Then you skip the nucleation phase and you immediately elongate. That's how we prove there is nucleation. And the disassembly pathway, I will show you now, you start with big colloidal assemblies and they have to go all the way to the monomer. So how does this happen? We did, again, kinetics. So this is called stopped flow kinetics. You mix the reductant and the assemblies very quickly, and you put them in a chamber, and then you follow the signal over time. So this is a semi-log scale. So in the first second, there's a very fast process, and then it's followed by a slower second process. So what actually happens is you have the colloids, you add the reductant, the surface reacts almost immediately, but then it takes some time to dissolve the whole colloid. So that's why this second process is much slower. Sorry, it's a lot of details in a very short time. But the overall reaction cycle is like this. So this is the oxidation step, nucleation, assembly, disassembly. That all happens at the same time. And one of our collaborators, Michael Stisch, he actually developed a model for this, which I think I will skip. But the result of it is indeed you have this window where you can get supramolecular size oscillations that we found in the model. And actually it turns out, or we think that this is quite general. So any supramolecular polymer that is cooperative and you couple it to something that destroys the polymer could oscillate in principle. Okay, so now the rest of my talk will be much easier. So we did some fun experiments like put monomer in a chip and put some preformed polymers here to try to get a traveling wave. So we did this, and yes, indeed, we find a traveling wave. So we talked to experts in the field of frontal polymerization, it's called, and they said, well, the wave should move with constant speed. So we measured the speed, and of course it's not constant. So here, this is a kymograph, so it's distance versus time, and the wave starts fast, and then it slows down, it stops. So what's actually happening in the experiment, you see the background is going from kind of yellowish to more pink. So in the background, you also have nucleation and self-assembly occurring. So actually the driving force for propagation is decreasing over time. That's why it's stopping. Then we measured the speed of the wave, and it was about a factor 100 faster than we expected. So this was also strange. So it turns out that the three different states, right? So this is the self-assembled state, this is the monomeric neutral state, and the monomeric dianion state have slightly different densities, but very tiny. I mean, you see the numbers on this axis, it's almost nothing. But apparently it's enough to drive convection. So when you have a horizontal layer and you have density differences, it's always unstable. Okay. So what we did is we put this now in a chip. Again, so you're looking at monomers, and we just let it nucleate by itself. And what you see is over time you get this kind of mosaic pattern formation. So what happens is there are random nucleation events. It starts elongating, it starts changing the density, which makes a convection cell, which then all these convection cells start fighting with each other, which results in this mosaic. So this was kind of nice. And then we said, okay, let's not try to fight convection, let's make it worse. So we replaced the top glass with a liquid, with oil. And then what you get is something, I really like this movie. So you have a kind of a point here where the system starts oxidizing, starts self-assembling, and then the whole cell turns into one big convection cell. This is 5 by 3 centimeters, is this size. It's really big. And the whole thing kind of makes one massive convection cell where now the supramolecular polymers, they kind of align in the flow lines of these things. And so these are really what I would, what Prigozhin would call dissipative structures. So they are non-equilibrium structures that make patterns on huge length scales, like much, much bigger than the molecules. Okay, so this is the conclusion of the first part. I'm still kind of on time. So I hope I've convinced you so far that putting self-assembly and chemical fuels together is kind of interesting. So the second part is about microfluidics without walls. And so probably you know microfluidics. It's basically trying to scale everything down, and it has a lot of benefits, but it has also quite a number of problems. One problem is if you look at the surface to volume ratio. So if you do a typical lab experiment, your surface to volume ratio is like something like 80. If you do the same reaction in a microfluidic device, you all of a sudden have a huge surface of walls and not a lot of bulk. So if you have a molecule that likes to stick to your wall, then you have a pretty big problem in microfluidics. So this is a typical thing you can get in microfluidics. So you can get clogging, fouling, and also the pressure drop scales with 1 over the channel radius to the power 4. So if you go smaller, the pressure needed to push the fluid through the channel increases really, really, really fast. Okay, so there are some approaches, of course, to get over this. This is from the Eisenberg group at Harvard. So they make these very beautiful coatings, which the first generation they called it slips, and the second they call it flips. So it's the same thing, but with a ferrofluid that is perfluorinated. And it basically reduces the drag of the surface because you get a microscopic liquid layer at the interface. Another approach is playing with the wetting of the channel. So here they use this photopatterning to make hydrophobic and hydrophilic patches, and then the fluid will preferentially go, in this case, in the hydrophobic part. A lot of new approaches are coming up. So this is using surface pinning. So you basically write with a pen of liquid on a surface, and the fluid spins to the interface, and then you cover it with the fluorinated oil, and you can draw your own, they call it freestyle fluidics. It's pretty nice. And then this is from one of my friends at Lawrence Berkeley National Lab. So they managed to 3D print a liquid in a liquid by having this surfactants at the interface. So our inspiration it's a very strange story. It comes from a concept that was introduced many years ago, which is called magnions. And I didn't like, what is a magnion? So it comes from this experiment. So this is a steel ball bearing dropped in acid in a magnetic field like this. So there's a field here. You see this blue stuff here coming out. This is actually iron that is reacting with the acid, and it's being released. It's paramagnetic, and it stays in these lobes of the field. But if you talk to the physicist, then they say, if you calculate the magnetic energy of one ion, it's like 1,000 times lower than kT. So there should be nothing, but there's something. So there's a lot of weird things going on in these paramagnetic fluid interactions. And one of our collaborators, Mike Coey, he's really a big guru in magnetism, and he was building on the work of Aogaki, who was a Japanese professor. And he introduced this concept of magnetic liquid confinement. So in this experiment, you see a magnetic field in this direction. You have a ferromagnetic track, so it makes a local magnetic field. And if you put a paramagnetic liquid here, it will follow this track. You can do also something called an antitube. So now he puts the field horizontal, so you will make a return field here that kills this big magnetic field here. So you make a magnetic hole. And if you make a magnetic hole and put a non-magnetic fluid, it will preferentially go there. So this was kind of where I got really excited because it's a liquid and liquid device without any physical walls. So I thought this must be very useful. So in his experiment, so he uses this huge electromagnet. This is a ferromagnetic track, so a wire. And you see here the liquid tube, but it's really huge. It's like millimeters. Okay. I'll skip this. So the drawbacks of this first approach was you need the huge magnets, you use toxic ions like holmium, and you can only do a straight channel. So this is where we started collaborating to make version 2.0. So we wanted to go to very cheap magnets, non-toxic fluids, and we want to do basically any geometry we want to do. So ferrofluids are these very interesting fluids that are, it's a dispersion of magnetic nanoparticles in whatever medium, can be oil, can be water. And so we make our own ferrofluids that are very, very strong, so you get these nice spiky things which look good. But then this is where basically we started. This is a dish of water, and here you have a magnetic track of little magnets that just point upwards. And when you extrude the ferrofluid, it follows the magnetic track. So the magnet is below the dish, right? So there's just a magnetic field. And this was, okay, it looks very cool, but it's completely useless, of course, because you have your fluidic channel, which is full of ferrofluid. So, and ferrofluid is sticky black stuff, so cannot do anything. So we wanted to make the inverse of this, so an anti-tube of using a ferrofluid. So it took us quite a long time to figure out how to do that, but in the end we figured out that you can make a magnetic quadrupole. Right? So you take 4 magnets, 2 like this and 2 like this, and this is a simulation. So blue means high magnetic field and yellow is low magnetic field. And if you do that and you inject ferrofluid, it will go on the outside and it will leave a magnetic hole where you can put whatever other thing, in this case water. Right? So this works really well. The problem is that ferrofluids are incredibly black. So the previous image we were imaging from the side, but it's quite limited. So we decided to build our own X-ray imager. So my uncle is a dentist, so we got a dental X-ray unit. And so our devices look like this. So you have magnets here and ferrofluid in the middle, and then we image with X-ray, and we can see here water surrounded by ferrofluid, and then some plastic, and then magnets. So we can indeed make these channels. And they are very interesting because they are naturally anti-clogging. We never managed to clog any of them. So here you see a 500 micrometer tube, and we put a 2 millimeter bead in the channel. So normally that's the end of your chip. But here we apply a little bit of pressure and we can push the bead out with 10 millibars, which is very, very, very low. So because the wall is magnetic, it can stretch and it can go back. Also, they're self-healing, so we put a plastic spatula through the tube from the top, which you see here. This is the spatula. And then when we take it out, it's broken, but you wait like 30 seconds and it will merge back because it's stable at equilibrium in this case. So the tube just self-heals when you break it. Then, because there is no wall, there is almost no friction, which is also kind of surprising. So we did this experiment. So these are 3 cups of honey, and we have a normal plastic tube of 1 millimeter. We have no tube, so just a hole, or we have our anti-tube with magnets and ferrofluid. So this was kind of surprising. So if you look, this is accelerated, of course. So you see that the normal plastic tube almost has no flow, right? It's just going to drip once in a while. The one with the hole is quite fast, but actually ours is even faster than the one with the hole, which is strange, right? So the reason is that we have no friction, but the driving force for flow by gravitation is the height of the liquid. So if you have more liquid height, you have more pressure. So here we have 4 centimeter, and here we have 14 centimeter. The same as here, but here you have huge friction. So the combination of having more honey and no friction causes actually ours to go even faster than just dripping in air, which I found very strange. So now we recently understand a little bit better how this flow works. So if you look, let's say the honey has actually a plug flow. So normally when you have a channel, you have a no-slip boundary, so you have 0 velocity at the wall, and you have Poiseuille-Perot, so you have this parabolic profile. So in our device, you have plug flow of your fluid, and you have a counter current flow, so the first layer of ferrofluid is being dragged by the honey, and then on the outside, there's actually a reverse flow of the ferrofluid. So the ferrofluid kind of goes around like a conveyor belt, and the central fluid just kind of goes through without any friction. We can make them quite long, so this is a 1 meter liquid tube, so we put, just for fun, we put some light in here and it comes out at the other end, so we can use it as a waveguide. You can make very different magnetic confinements, so you can make a single tube, or you can make 2 tubes, or you can make 3 tubes, depending on the positioning of the magnets. So we're trying to go to see what is the smallest thing we can reach, because like I told you, the delta P scales with 1/r⁴. So if you go to very small channels, the pressures become incredible, right? So this is a liquid tube of 85 micrometers that we imaged with X-ray tomography in Zurich. So we can make them very small, and actually our record tube now is at 16 micrometers of what we can see. There are smaller ones, but we cannot see them anymore. So this is our model, and these are all the tubes we made. So we can make them, from millimeter size down to micrometer size. So that's kind of where we're heading, like trying to make these nanofluidics. But then, let's say, a side effect of this is you can play with the tube in other ways, right? So this is the simulation of a normal liquid tube, and if you add other magnets here, in this case, you can magnetically squeeze the tube. So you can actually cut off the flow, so you can make a valve. And a natural extension, let me skip this. Natural extension of this was, okay, if you can squeeze the tube, maybe you can move the pinching point along and you can do pumping, because that's how a peristaltic pump works, right? You pinch and then you move it around, and that creates pumping. So we made this device. So here you have a quadrupole with a water tube here. These are these pinching magnets that kind of will move around. And you see that if you turn this wheel, we can indeed pump some water. So so we call it magnetostaltic pumping, because there's no physical contact between the magnets and the liquid tube. It's all used on magnetic forces. This looks good, but the pressure is very low. It's like 20 millibar. Okay, so you can pump some 0.5 milliliter per minute with 20 millibar. But since we have already improved, so this is a later prototype where the flow rate is now much higher, and so what we're commercializing now, this is our company, Q Fluidics, that now has our first generation pump, which produces 1 bar and 50 milliliters per minute. So it starts becoming reasonable. We can also make smaller ones and bigger ones. So our highest pressure is now something like 3.5 bars. So it's pretty high. So another part we're working on is, of course, a limitation of this technology is you have contact between whatever is flowing or pumping and your ferrofluid. And most commercial ferrofluids, they are based on kerosene. And kerosene is not a super nice solvent. So we have now a class of ferrofluids that are completely perfluorinated, so they are completely inert. They're immiscible with almost any organic solvent, and with water, of course. And so we can combine now these compatible biofluid or ferrofluids with our pumping technology. And so what we're pursuing at the moment is pumping of biological fluids. So because you have this liquid-liquid deformation and you have a slip boundary, I showed you have this plug flow. And plug flow means that all the velocity is the same. So the shear rate, which is the derivative of velocity, is very low. And so shear is what breaks stuff, right? If you flow blood through a peristaltic pump, you get this. So this is the blood plasma. You put it through the pump. The red blood cells, they are sheared, they break, they release hemoglobin, and your blood plasma will turn red. So this is when you go to the hospital, hopefully you never have to do this, and you have a heart surgery, they disconnect your heart, they put it on a peristaltic pump for a couple of hours, and then they put it back. And then basically you sheared the blood so hard that all the platelets are activated, red blood cells are broken, and it's amazing that you even survive it, but you do. But we think it can be done better. So here you see, this is kind of preliminary result of blood plasma when you just get donor blood and you just centrifuge it. So you have no hemolysis. This is after our pump, and this is using a peristaltic pump. So we think we can do this kind of low shear pumping, and hopefully we can do something relevant in the clinic. So with that, that's the conclusion of part 2. So we have made this kind of wall-less fluidics approach that is scalable from centimeters to micrometers. You create self-healing, uncloggable channels, very low friction, plug flow, which is interesting for analytical applications, and low shear pumping, which we're trying to commercialize right now. So this is the group. So the first part was done mostly by Alessandro Sorrenti and Jorge, who's here. And the last part, the microfluidics, is mainly developed by Taki, Peter, and Arvind. This is the funding. And thank you for your attention.
Thank you very much, Thomas. Now we can get some questions. Monica, yes, please.
Fascinating. How small you can make
The channels? Right, so what we have been able to image was 16 micrometers. But then if you put more ferrofluid, it becomes smaller. So we see nothing on the camera, but water still can flow through. So there is...
Even if it's like really breaking?
Yeah, so the breaking, it depends on the susceptibility, magnetic susceptibility, and on the surface tension. So if you add surfactants, you can get smaller tubes. In some cases, we see breaking up of the tube, so that then we know that's the real limit in size. Yeah. But according to our models, we should be able to go below 1 micrometer.
And with the perfluorinated or whatever,
yeah.
Then you can actually make it rather smaller, right?
So the perfluorinated has higher surface tension, at least with water, so that they're bigger actually. But if you add, again, if you add surfactants, because it's a balance between the Laplace pressure and the magnetic pressure.
I do have a question indeed. So for this ferrofluid walls that you have, which are sort of dynamic, they do have a flow. Is it possible to reverse that flow as well?
To reverse the flow?
You went from no slip to slip boundary. This is like extended slip.
Right. Maybe, because at the moment we're not actuating the ferrofluid. It's like the ferrofluid movement is a result of what is flowing through the core region. But there you could maybe do like magnetohydrodynamic flow, which is used for ferrofluids also to create a flow in the ferrofluid, which then drives the core fluid or creates a longer slip length, effective slip length.
That will probably introduce a lot of new physics into this whole thing.
Yeah, it's quite difficult. I mean, for me, fluid dynamics is already complicated, and then ferromagnetohydrodynamics is like, it's pretty tough. Yeah. We're trying to set up collaborations now.
So a defining feature of non-equilibrium systems is the presence of fluctuations. And in fact, what happens to them as you go far from equilibrium. So it was a little bit interesting for me because you introduced it through the logistic map, which is famous for being deterministic.
Right.
But that's when I think you were taking some pedagogical license.
Right.
So my question is, have you actually looked at what happens to fluctuations in your system because you use this light scattering technique to determine the size? I think you should have access to the data for the fluctuations of the size as well. Have you looked at what happens in the scale?
So,
disassembly to assembly line?
right. Short answer, no. The long answer, yes, of course, would be interesting, but so we are aware of all the, let's say, the majority of the physics community is in this like small systems and looking at fluctuations. My background is more from bulk chemical oscillators, so you use huge volumes and try to look at that. So we haven't really made that bridge to pulling in fluctuations in our systems. So we're really like at a kind of, also the models are kind of just kinetic model, chemical kinetics model. So it's all bulk ensemble, like very large scale assumptions. But yeah, it's definitely interesting suggestion.
Well, maybe slightly related to Monica's question, I was thinking of your ferrofluidic system where imagine you have single molecules somehow captured and applying your magnetostaltic pump. Wouldn't you be able to push all the molecules out even if you don't have
in principle, should it be possible even to have the system to work at a single molecule level?
That's a good question. I mean, at some single molecule, I don't think so. Because well, actually, the tubes can also work with gases. So we don't need a liquid core. We can even pump air with our pumps. But there will always be a balance between surface tension of the ferrofluid and your magnetic pressure. So you will probably make very small compartments, but like a single molecule scale, I don't think we can reach it. But maybe I'm misunderstanding your question.
Well, you're the expert,
yeah.
So we'll talk out.
Okay, we can talk.
Yes, I could.
It's a great talk. So, when I listened to the first part of your talk, this post-formulation, the molecular process, this automatically reminded me biological systems, cell division and stuff. You have chromosome, that euchromatin becomes heterochromatin, and you go from interphase to mitosis. So, do you have any comments about the implications of your experiments?
Right. So one thing we are really lacking in our artificial systems is a way for so we can make an oscillating polymer now, but we have no way to attach it to something. And if you want to do any biological like functions, like microtubules can attach to something and then they can pull or they can push, and this is something we're kind of lacking. So we have just these supramolecular polymers swimming in solution, oscillating. But it would be really nice, we're trying to work on that to attach them to certain things, which then it turns into mechanical or materials properties. So this is, I think, the link that is missing when you compare it to biology.
I have a second question, quickly. So for the second part, have you tried any polymeric liquids, like to make that flow through your
Not, well, actually, yes. So we did photopolymerization, so we pump monomers and we use a transparent magnetic fluid. So we also have a patent on this. So you can actually put UV light and you flow monomers, and because there's no wall, it cross-links, and then you can just pull the stick of polymer out at the end. So we're trying to see what is a real useful application for that. But I think mainly it will be like in viscous liquids are difficult to pump also. So we're trying to evaluate. Yeah, let's see. Yeah.
Yes, please.
You mentioned about distributive systems that your first work on. What is the requirements for a system to be dissipated other than it should work on far from entropy?
Right. So what our community is kind of doing is using these chemical fuels, and then you say, well, you consume a fuel, so therefore you dissipate chemical energy. So it's kind of, but there are systems, also like Serim is working on that, where you use different methods that are not chemically, inducing, and then it's more. Yeah, physical. It's more difficult to define. It's more difficult to define where you are in your if you are dissipative or not, or if it's like some systems you have a time varying potential, but you can still describe it with an equilibrium simulation because you basically make an effective potential, which then organizes your system. So then this discussion becomes more complicated. So we chose the easy path of chemical fuels. It's irreversible process, so dissipative. Yeah, but it's not 100% defined, let's say.
Okay, then. If there are no other questions, let's give Thomas a final round of applause. And we do have the lunch break. I hope you have been holding on to your lunch coupons, as I do. Lunch will be served next to the pool. That will be in that direction, and we'll be meeting back at 2 p.m. By the pool, yeah.
Excellent. Great. I have been doing a lot of microfluidics, and I did some microfluidics, but it was really nasty, and then I couldn't put any two fluids next to each other, and then I gave up. This is a very good